Dear students, this is Professor Manoranjan Singha, Department of Mathematics, University of North Bengal, India. At the end of the last clip, we have seen that sequential compactness implies countable compactness, and countable compactness implies limit point compactness in general. And in that clip, I have claimed that if we confine ourselves within first countable T1 spaces, that is, if we consider only first countable T1 spaces, then these three kinds of compactness will be equivalent. That is, the picture will be like this: sequential compactness, countable compactness, and limit point compactness same topologically. That is, collection of sequential compact spaces, collection of countable compact spaces, and collection of limit point compact spaces will coincide in case of first countable T1 spaces. So we are getting a result like this, that in case of first countable T1 spaces, sequential compactness, countable compactness, and limit point compactness are equivalent. Let's prove this result, and I will sketch the proof as I do generally. So in general, sequential compactness implies limit point compactness. That is, the family of all sequential compact spaces is a subfamily of the family of limit point compact spaces. Now, if we show that limit point compactness implies sequential compactness, so this family and this family will coincide. So these three families automatically will coincide. So we will get this picture. So it is sufficient to show that limit point compactness implies sequential compactness in this situation if we confine ourselves within first countable T1 spaces. So it is sufficient to show that limit point compactness implies sequential compactness, because sequential compactness implies countable compactness, countable compactness implies limit point compactness in general. So it will hold in this particular case also. Now if we show this limit point compactness implies sequential compactness, that is, if we show this, from this we see that these three will be equivalent. That is, if a first countable T1 space is sequentially compact, then it will be limit point compact as in general case. If a first countable T1 space is limit point compact, then it will be countable compact, sequential compact. So all these three will be equivalent. So let X be a first countable T1 space which is limit point compact. We will show it is sequential compact. That is, we will take any sequence in X and we will find a convergence of sequence in X by using this fact that the space is first countable T1 and it is limit point compact. So let Xn be any sequence in X. Then two cases may arise. One is the range of this sequence is finite. Another is the range of this sequence is infinite. Now if the range, range of the sequence is written in this way. So if this range is finite, then that finite number of points are scattered over infinitely many terms, countably infinitely many terms of this sequence. So at least one point of this range set will be repeated infinitely many times over countably infinitely many terms of this sequence. So we will get a constant subsequence of this sequence. So if this is finite, then this sequence has a constant subsequence, and since it's constant, so it will be convergent. We know every constant sequence is convergent, every constant function is continuous, like this. Then this sequence has a constant subsequence which is convergent. So in this case, when the range is finite, we are getting a convergent subsequence of this sequence. Now let's see what happens if we consider that the range is infinite. So if this range of the sequence is infinite subset of the limit point compact space X. Fine. So if this is infinite subset of this limit point compact space, by the definition of limit point compactness, every infinite subset of X has a limit point. This being infinite, it has a limit point. So if this is infinite subset of the, then this range set, this has a limit point, say small x and capital X. Now one may think that X being a limit point of this set, so X belongs to this, up to this it is correct. But if you say that since X belongs to this closure, so there is a sequence in this set that converges to X, and by some manipulation, by some rearrangement of the terms of this sequence, we can get a subsequence of this sequence Xn which converges to X, but it is not the case. Actually, for this we need T1 property with this first countability of X. So I am not going to use this fact that if X in this closure and the space is first countable and T1, then this kind of rearrangement of the terms is possible, so that the rearranged sequence will become a subsequence of these as well as it is converges to X. I am not using this fact. Let's prove it directly. Let's find a subsequence of this sequence Xn that converges to X. Let's prove it directly. Okay, so since X is first countable, so it is first countable at each of its point, that is first countable at the point X. What does it mean? It means this X has a countable base. Okay, and the X has a countable base at small x. So since X is first countable, so there exists a countable base, say beta X. Since it is countable, we can write it in this way, indexed by the set of natural number. Countable base, say this at x. Now countable base means base at x means whenever we take an open set containing x or a neighborhood of x, then this open set or neighborhood will contain a member of this beta x. Okay, you know this definition of countable base at a certain point. Okay, now by using this sequence of open sets each containing x, let's construct a new sequence of open sets like this. So let Vn equal to the intersection of first n members of this beta x. If we arrange the terms, the members of this family in this way, u1, u2, u3 in the ascending order of the indices. So we should write in this way ui are equal to 1 to n. So every Vn is finite intersection of open sets. Okay, so every Vn is open. Okay, then every Vn is open. Now every un contains x. So every ui contains x. So this intersection contains x. So every Vn will contain x. So x in Vn and if we just consider Vn plus 1, then the range will be equal to 1 to n plus 1. So one more member of beta x will participate to this intersection. So this intersected portion will be a subset of the Vn. So Vn plus 1 subset of Vn, and it will hold for every n in n. So we are getting a new sequence of open sets Vn, v1, v2, v3 in this way, each containing x satisfying this relation. That is, whenever the indices of Vn increases, the size of the set will decrease. Fine. Okay. Now, in particular, x being a member of Vn for every n, so x in v1. So this is an open set containing x, fine, and x is a limit point of this set. So this v1 will contain members of this other than x. v1 will contain some member of this other than x. v1 may contain many members other than x. Okay, but every member indexed by set of natural number, and set of natural number is well ordered. So we can get a member having least index that not equal to x and contained in v1. So there exists a least positive integer n1, say, such that this x n1 not equal to x and x n1 in v1. Fine. Okay. Just a minute. Okay. Now, since here is the place where I am going to use the T1 property of x. We have already used the first countability of x. Now this is the place where I am going to use the T1 property. Since x is T1, so every finite subset of x is closed. Okay, so this v2 minus this x n1, This is closed, this is open. Open minus closed, that is open intersection, this closed complement, that is open intersection open, that is open. So this is open. So this is an open set. This is an open set in X. And B2 contains X and xn1 not equal to X. So X is not deleted from B2. X is in B2. So X still in this open set. So this is also an open set containing X. Since X, so X in B2 minus X n1. Again, since X is a limit point of the set, this, so this set will also contain an element of this set other than X. Fine. So there exists again a list positive integer n2, and we can choose n2 greater than n1 such that X is not equal to xn2 and xn2 in b2 minus this xn1. Fine. So in this way for this set, this vk, similarly X will be in vk minus xn1 xn2 dot 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 xn k minus 1. This is finite, so it is closed. vk is open. Okay, so whole thing is open. This is open set containing X, so it will contain, as simple as that. This is open, so there exists a list positive integer nk greater than nk minus 1 such that X is not equal to xnk, and this xnk in this n1 xn2 dot 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 xn k minus 1. Fine. So in this way we are getting a subsequence x and k. We are getting a subsequence x and k of this sequence xn. Now the claim is this subsequence x and k will converge to this x, that limit point x of this x and k will converge to this limit point x. This is my claim. So the claim is this x and k converges to x. Simple claim. For let u be any open set in X containing X. Okay, containing X. Okay, so I said that since this beta X is a countable base at X, so whenever U is an open set containing X, this open set will contain a member of this. This is the definition of countable base. Okay, so there exists a member, say un in beta X such that, so un in beta X, so X in un such that this un contained in U. Fine. Good. Now if k, this k, greater equal to this capital N, then let's see what happens. Then U contains UN and UN contains Vn. Why? Because Vn equal to intersection of Ui I equal to 1 to this capital N. So U capital N is a participant to this intersection, and we know every participant is larger than or bigger than this intersection. Okay, so UN being a participant to this intersection, so UN will be larger than this intersection. So this, fine. We also noticed that this, where this one, and I said whenever indices increases, then the size of the set decreases. Okay, so in this way we can write this is V n minus 1, this is greater than this, so this is smaller than, so when okay, no, not n plus 1, fine, n plus 1, since it is greater than this, so the size of this set will be smaller than this one, fine. Similarly V n plus 2, so in this way dot 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 dot, we will get V n plus n minus k, no, k minus n, fine, k minus n. So it is basically Vk. Okay, and from this we see that Vk contains xnk. Okay, xnk in Vk but not here. Okay, so xnk belongs to this. So ultimately that is xnk belongs to u if k greater or equal to n. So for any open set u containing x, we are getting a natural number capital N, so that whenever k greater or equal to capital N, all x and k enter within this u. So x and k converges to x. This is the definition of convergence. You know very well. Okay, so we can write x and k converges to x. Thus what we are getting? We have started with any sequence xn in x, and we are getting a subsequence xnk of this sequence that converges to x. That is, this is convergent. So since this sequence is arbitrarily taken in x, so every sequence in x has a convergent subsequence. Okay, thus every sequence in x has a convergent subsequence. Fine, and consequently x is sequentially compact. Okay, so we are done. Fine. So we have proved that in case of first countable T1 spaces, sequential compactness, countable compactness, and limit point compactness are equivalent. Fine. Now let's see what happened if we remove just one condition from this, if we remove first countability, then see whether these three are equivalent or not. We will see that they are not equivalent. And we will see that if we drop this T1 property of the space, then also we will see they are not going to be equivalent. Okay, fine. So note first note is this. Consider this example, well known R tau ray. In the first clip we have discussed R tau ray. This is obviously first countable, and it is not T1. You can check easily, and you know, but not T1. And we see that it is limit point compact, but not countably compact. In the first clip, you can see not countably compact, and hence not sequentially compact. So actually these three are not equivalent. Let's use another example, I raised to I. This is T1 because I means closed boundary interval 0, 1. Since R with usual topology is T4, so T1, and this T1 property is hereditary, so any subspace of R will enjoy this property, so this is also T1. And we know T1 is productive property, that is product of T1 spaces is T1, so this being a product of this, so this is T1. Fine, but you can check, but it is not first countable. It is not first countable. Fine, it is not first countable. So what we are getting, it is T1 but not first countable, and as a result we see that you can see in the first clip that it is limit point compact but not sequentially compact, isn't it? But not sequentially compact, and so it cannot be countably compact. No, it is countably compact, limit point compact but not sequentially compact. So these three are not equivalent. Fine. Okay, so next note, and it is important, very important. Okay, which is actually we know metric spaces are first countable. Metric spaces are first countable, and T4, so T1. So metric spaces are first countable as well as T1, and we have seen in the last result that in case of first countable T1 spaces, all these three, limit point compactness, countable compactness, sequential compactness, are equivalent. So in case of metric spaces, okay, so in case of metric spaces, this sequential compactness, countable compactness, and limit point compactness are equivalent as a consequence of the last result. Okay, in the next clip actually we will see that in case of metric spaces, actually all the four kinds of compactness that we have discussed, compactness in classical sense, sequential compactness, countable compactness, limit bound compactness, all will be equivalent. In case of metric spaces, compactness, sequential compactness, limit bound compactness, countable compactness, all are equivalent. Okay, we'll see. That is, in general, we got this picture. Then in case of first countable T1 spaces, we got actually this sequential compactness, countable compactness, limit and complex spaces. And if we consider metric spaces, say this is the family of all metric spaces, the family of all metric spaces. Okay, then actually we will see that family of compact spaces, that is family of compact metric spaces, family of sequentially compact metric spaces, family of countably compact metric spaces, family of limit bound compact metric spaces, all will coincide. That is, all are equivalent. So in case of metric spaces, we can define compactness by using the definition of sequential compactness. That is, we can say a metric space is compact if and only if every sequence has a convergent subsequence. Okay. In case of metric space, we need not take actually arbitrary open cover. It is sufficient to take just countable open cover. If every countable open cover has a finite subcover, then the metric space will be compact. Okay, so it reduces the labor, isn't it? The limit point compactness. By using this, we can define compactness in this way. That is, a metric space is compact if and only if every infinite subset of that metric space has a limit point. So we will discuss all those things in the next clip. Okay, thank you.